Okay, so we've been working with the dot product. And if you have two vectors A and B, and you take the dot product, the answer you get is just a number with units. It doesn't have direction. Magnitude only. And the way you get that number is you take the part of vector A that's in the direction of vector B, and you multiply that by the magnitude of vector B. We actually calculated dot products last year when we calculated work problems. If you look at this work example, you have some force that's pulling the box forward. There's other forces acting on that box. Fg, maybe a friction force, a normal force. But we're just focusing in on some forward applied force at some angle theta. And one of the things we have to do sometimes is calculate how much work did that force F do. But not all of F, not all 10 newtons, is pulling the box forward, but yet the box is moving forward. So to calculate the work done, you can't just say 10 times 2 and get an answer of 20. That would not be the right answer. Now, this is kind of interesting. Notice the forward displacement is denoted with an S. That's very old school. Like when I was in high school, both distance and displacement were denoted by the symbol S. Now it's usually denoted by the symbol X. But even in your textbook, and even in your AP Course 1 textbook last year, when it came to calculate work, the tradition is to still use the symbol S to represent displacement. So if we wanted to calculate the work done, the official definition of work would be it's a dot product between the force and the displacement. And we could simply write this out, F dot S. That signifies we're going to take the part of F that's in the direction of S and multiply it by the magnitude of S. So if I break that F up into parts, part of F is acting this way, part of F is acting that way. This is the part of F that's parallel to S. This is the part of F that's perpendicular to S. And when push comes to shove, if we want to calculate that dot product, we would take the part of F that's parallel to S and multiply it by the magnitude of S. So take a moment and figure out that answer. Do you need the data again from your previous page? So the component of F that's parallel to S can be found by taking all of F, which was the 10 Newton force, and multiplying it by the cosine of, that was 30 degrees, yes? Yeah. And then multiplying that by the magnitude of S, which was 2 meters. And when you crunch that out, you get 17.3 newtons times meters, which equals 7.3 joules. And that doesn't have direction. It's a scalar quantity, the amount of work done, 17.3 joules. So, in that example, if theta was 0 degrees and the whole shebang force was exactly in the direction of the displacement, then determine what the work would be. If theta was 90 degrees and the force was straight up and the object was moving horizontally to the left, then determine what the work would be in that case. In the first case, what would the total work be if the angle is 0? Jason? 20 joules. But in the second case, if that force was straight up, David?
0 joules.
0 joules. And we saw it in the calculation, but just let's emphasize this. Which trig function is a maximum at 0 degrees and 0 at 90 degrees? Brandon.
Cosine.
Cosine. So it turns out that the cosine trig function is a big part of doing the dot product. Now, we could have written it out like this. No. Yeah, we could write it out like this. A dot B is equal to A parallel times the magnitude of B. But it turns out that the parallel part of A is always equal to the magnitude of A times the cosine of theta. Where theta is the angle between vectors A and B. But usually, the cosine is brought out to the right, and that brings us to the official formula, which I told you I could have just presented in 30 seconds. If you want to calculate the dot product, A dot B, you just take the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. If you wanted to write it out more formally, you could use those double absolute value signs, which stand for magnitude. A dot B equals the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. So this is the official formula for the dot product. So I want to give you a problem where you're going to determine the dot product, and if you want to use the official formula or, your gut understanding, back up to this and see if you can come up with the right answer. So an object is being displaced 3 meters as shown. While it's being displaced in the direction shown, there's this force of 20 newtons acting on it. Now, there has to be other forces acting on the object, otherwise it wouldn't go in a straight line the way the 3 meters is shown. But we're not concerned about that. Yes, there's other forces acting on it. All we're concerned about is during this process, as the object moved along this 3 meter displacement, and that force acting the way it's shown, acted on it, how much work did that force do on the object? So the work done by the 20 Newton force is the question mark. Now, as soon as you get your answer, check in with your table partner, make sure you're on the same page, make sure you agree. And then, I want to continue forward because there's another formula for calculating the dot product. And I have to be honest with you, this next formula, to me, it's not quite as obvious as the first one is. But you have to use the other one probably just as often as the first one. So, I want to lead you up to this next formula, but first you have to do some preliminary work. So I'm going to ask you to answer these questions on the next page, and then check in with your table partner and see if you're getting the same answers. Now keep in mind, the unit vector I has a magnitude of 1. If I wanted to find the magnitude of unit vector I, it would be 1. And keep in mind that a dot product, A dot B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Keeping those two things in mind, don't shout out the answers, answer these next 3 scenarios. That's the first one. The second one, you're going to figure out the dot product between unit vector I and unit vector j. The third one, you're going to take the dot product between I and negative I. Now in a second, I'll come around and I'll give you thumbs up, thumbs down on these three answers. But for now, you could just check with your table partner, see if you're in agreement. Because we're going to use this, folks, as we go forward and take the dot product of two three-dimensional vectors. So, moving forward, So we have vector A and vector B. They're both three-dimensional, and they can be expressed in terms of their x, y, and z components. For example, vector B can be expressed as the component of B in the x direction times unit vector I plus the component of B in the y direction times unit vector J plus the component of B in the z direction times unit vector K.
Where's unit vector B?
What's that?
Where's unit vector B?
It's that little thing, that little.
Where's the vector B?
Unit vector, yeah.
There's no unit vector B drawn. There's just vector B.
Yeah, vector B, that's what I mean.
Vector B starts at the origin and headbutts
Go down.
the last vector added. Now remember, this is a three-dimensional picture here. And the magnitude of that vector B right there is actually going to be bigger than bx, by, and bz. But the way I had to draw the picture, it looks smaller, but it's really not. It would actually be bigger. You know, it's a three-dimensional plane. And you know, here's vector A, starting from the origin, headbutting the last component. Yes?
How come you drew it so that z is pointing up and like not forward towards us?
I'm more comfortable that way.
Oh, okay.
As long as it's a right-hand coordinate system,
It works.
it works. All right, so what we need to do is find an expression for A dot B, vector A dot vector B. You all ready for this?
Oh, no, I'm
Y'all ready for this?
So I could rewrite A as AX times I plus AY times J plus AZ times K. And then that's going to go through the dot product with vector B. Bx times unit vector I plus by times unit vector j plus bz times unit vector k.
Oh my god.
Now you know what's going to happen next, folks? We got to do it. We got to FOIL it out.
Wait, what?
We got to actually write this out.
Oh no.
So the first one, that would equal ax times unit vector I dot bx times unit vector I plus, and I just have to keep like distributing. You know, some people call it foil, some people call it fireworks. The next term would be AXI times, or dot, BYJ. And you just have to keep going through. Now, as you go through this, folks, you might want to keep in mind some of these have an answer. Can anyone read your physics teacher's mind? David?
Some of them are going to be 0.
Some of them are going to be 0 because like one of the answers on this was 0. So as a matter of fact, quite a bit of stuff does. So you need to keep in mind this answer right here and this answer right here as you simplify this out. So go ahead and expand that, but keep in mind, if you have a unit vector dot itself, you should know what that answer is. And if you have a unit vector times a different perpendicular unit vector, you know that answer. So I want to see in your call, I'm going to come around, show me the answer to those 3 unit vector dot problems, and then expand this out and apply those rules to this and see if you can come up with a simple handy dandy formula for calculating the dot product of A and B. And like I said, it's not very intuitive to me, but I believe it because I see where it comes from. So you could call me over if you have that bottom line formula. This simplifies to be ax bx plus ay by plus az bz. That's a formula you could use for finding the dot product when you can do it for 3-dimensional or 2-dimensional when you have the vectors written in terms of their unit vectors. Go back and try this formula with the U try problem and see if you get the same answer.
That's not the cross product. Look at the question. Not cross product. I know. No, I know it's different. U1, V1, 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 V2 minus U2, V1, comma, U2, 3, 1, 3, 1, 3. No, 2, 3, 3, 2. Yeah, it flips.